Starting the recording. Okay, so what we're talking about today is IP networking. Now, some of you may be more familiar with IP networking than others. And for those of you who are, that's great. For those of you who are not, that's what this class is for. So we're going to start talking about networking in general, and then we'll dig into IP, and then we'll talk about why it matters to amateur radio operators.
At the end of today, will we get our CCNA?
You will not get your CCNA.
You'd be lucky to get a comp.
You'd be lucky to get a pat on the back out of this. So yeah, I don't have any certifications. I have 35 years of experience, and whenever I tell people that I don't have any certifications, but I have experience with everything, they seem to be okay with that. So even though I don't have certifications, I still do a lot of things. I thought it went pretty well. They gave me a little programming test to do. I did that, but I haven't heard anything back yet. So I talked to the recruiter guy today, and he said that he would reach out to the hiring manager and find out what's going on and get back to me, but we'll see what happens. All right, so networking. The Open Systems Interconnect group developed this standard for describing networking, and this is like a overriding over everything standard. So any type of networking that you see or do or are involved with can be plugged into this structure. And we'll talk about how IP plugs into this a little bit later. But basically, the concept is that you have different layers in this stack, right? And each layer specifies the properties and protocols that are important at that layer. So the physical layer is like the actual piece of wire, or in the case of amateur radio, it's most likely an RF signal happening through the air, right? The data link layer is the low level, how things work on that wire. And then the network layer above that decides the physical path that data is going to take as it moves around the network. The transport layer is used to provide you with different protocols that are easier to write code for, but take advantage of those lower layers. So you don't have to know all the mechanics of the lower layers in order to write your program. You're writing to this transport layer. The session layer is something that is responsible for defining how different programs or different pieces of software figure out who to talk to, because you might have more than one server or client on a given machine. The session layer helps decide what goes where, okay? And then the presentation layer makes sure that that information is the information that you want to see. And then finally, the application layer at the top is where the applications live to access those services, okay? So we're going to hit some basic terminology first. We'll talk about some different words that we use in the context of networking. And if you run into problems or you get confused through the meeting, and I'm talking about something and you're like, wait a minute, was that a node or was that a port or what are we talking about? Just raise your hand or say something and we'll talk about it, because I want to make sure that people are getting the information that they need. But this is the basic structure or types of terms that we're going to use. A node is essentially some type of machine on a network, okay? A network is basically a connection of nodes, a way that nodes communicate with each other. An interface is the piece or the logical connection point between the node and the network. It may be a physical connection point as well as a logical connection point. The port is going to be, well, the port is that physical connection point. A router is a node that has multiple interfaces. It's on multiple networks, and it can decide which way traffic should go. So it'll receive traffic from one interface, look at that traffic, and decide if it's going to send it out another interface or other interfaces. Protocols they're basically a description of how things are arranged, and they allow you to make effective use of your network. A bridge is a physical device that is designed to extend a physical network in a single collision domain. We'll talk about collision domains in a minute. But basically, if you've got two physical networks and you have a bridge in between them, it essentially makes it look like one big physical network. Okay. A repeater is a way to extend that physical network with multiple domains, but a single logical network. So it looks like two separate physical networks, but all one logical network as far as the nodes on the network are concerned. Okay. And a hub is a device which is basically like a bridge for twisted pair networking. So if you think about your Ethernet twisted pair cable, you plug that into a hub, essentially that's one single network. Everything that's plugged into that hub is one single network. A switch is kind of like a repeater for twisted pair. It's smarter than the hub. It can say, oh, well, this wire is busy right now. So I'll hold on to that information for a second and then I'll send it out when I can. And it will only send it to the ports that it needs to go to. Okay. Yes.
And it's the full bandwidth between ports.
Yes.
A hub takes that 10
Typically,
meg hard drive.
everything is 10 meg for everything, right? Yeah.
But
With a switch, any two devices can get the full bandwidth of the network, right? Depending on the backplane of the switch. Dan.
And just to put a not too fine point on it, these devices don't really control it. It reads the packet, the incoming packet.
We'll talk about that.
Packet tells the router where
What to
it wants
do.
go.
Yes.
And so the router is the mechanism that says, okay, you're here, you want to go there. Are you allowed to go there? Do I have a route to that location, right?
Well,
And then
yeah.
they'll send it off.
We'll get to that point when
Yeah.
when we reach that level. Okay. So there's a few different types of physical network. You've got Ethernet. Ethernet is CDMA, which is collision detection, multiple access. Basically, the network looks like a bus. It's like a single piece of wire. Okay. You can have multiple nodes on that wire, and those nodes have to share access to that wire. So if a node wants to transmit, it looks at the wire first to see if anybody's already transmitting. And then if nobody is, it will start transmitting a signal while trying to detect if there's any collision, which, so you say two nodes start transmitting at the same time. As those signals meet, there's interference, and the node will detect that and discover that there's a collision there. And when it sees that collision, it will stop, back off some random amount, and then try again. The thought process is that two nodes won't back off the same amount. So one of them will get to go first, and then the other one will slip in.
Unless you're Cisco.
We're not talking about Cisco. As I said, we're not CCNA. This is not a CCNA class. Okay.
Now,
So-
another thing on the CDMA, it all, I mean, the port, you ask yourself, how does my computer know when someone else is transmitting? All that interface port is doing is looking at the voltage of that pair.
It's seeing if there's a signal
If the
there.
voltage is there, someone's transmitting.
Right.
If there is no voltage, and we're talking microseconds, okay, that these are listening for and he's listening, he's looking for a high voltage, right?
Right.
And so that's how he does a carrier detect. If there's a voltage on the line, he's gonna hold off until it goes through an algorithm, he then listens again. Oh, I have my time,
I'm going to raise my carrier.
Someone may do the same thing at the exact same time.
And then again, there's a collision detected.
And so you have now double the voltage on the line, and so they go through the process of say, okay, I'm gonna wait X amount and then I'll try again.
Yeah. And again, this is happening in the milliseconds, right? Not, not seconds. Yeah. Not seconds. It's like really fast. So another physical network type is token ring. Used to be used an awful lot back in the day. I haven't really seen any token ring networks except in IBM shops lately. And even then, it's only like old IBM gear.
FDI is similar to token ring.
Yeah, you don't usually see FDI anymore either. It's usually Ethernet over fiber now.
Yeah.
But yeah, so
The
the concept with a token ring is it's a mitigation method for who gets to use the network. And so there's a physical collection of bits that's considered to be the token, and that is passed around the ring. So it's a circular network. It goes around this ring from machine to machine. And when the machine gets the token, then it says, oh, I have the token. I have permission to transmit. It transmits everything it wants to transmit, and then it passes the token on to the next node. And then that node does the same thing. It's received everything that's come through. If it wasn't for it, it sends it on the other direction. And then when it sees the token, it says, now I can transmit my traffic and then pass the token on. So this token proceeds around the ring as it goes around. So one of the benefits, I guess, of token ring is that if a node disappears, then the two endpoints that surrounded that node can turn that around. And essentially your ring, instead of going around in a circle like this, goes around here, loops back this way, and then comes back down this way. So you can tolerate one node failing without breaking the network. I guess that's an advantage of token ring. The only systems that I've seen that really use token ring, like Dan mentions, FIDI, which was a fiber optic network, and the IBM systems use token ring, and then the Apollo domain systems used the token ring network. But man, I haven't seen an Apollo domain machine since the 80s, so highly unlikely you'll run into something like that. All right, so let's talk about Ethernet. Ethernet is the one that we normally work with. We do a lot of our networking stuff with Ethernet, and we'll get into more context of how Ethernet is used as we move on. But in Ethernet, there's basically some kind of physical medium or wire that is used to carry the signal, and it's a radio signal on that wire. So you can think of that Ethernet cable as being an antenna, essentially. And that's why it has to be terminated at both ends so that the bits don't leak out the end, right? But the original Ethernet design, well, and I say original, there was actually a network called Starland way back in, gosh, the 80s that was a 1 megabit per second Ethernet-y type of system that ran on twisted pair cable, and it was actually pretty cool. It actually worked, but hardly anybody uses anything like that anymore. You may encounter something like that in some weird industrial controls environments where equipment is 30, 40 years old, but you're probably not ever going to run into that. Thick Ethernet was RG8 cable. It's about maybe half an inch around. Or across, and the designation for that was 10^5. The cable could be up to 500 meters long, and the reason for the limitation was the particular frequency of the radio signal on the wire. You wanted to make sure you could get that collision back within a certain amount of time. Yes.
Thick meant was each node literally had to tap into it.
There were a couple of ways to do it. You could either cut the cable, put a connector on both ends, and put your transceiver in the middle, or the most common was the vampire tap. If you ever find a stretch of cable and it's got little black dots like every meter and a half on it, that's thick Ethernet, usually yellow cable with little black dots painted on it. And each black dot was a point where you could put a transceiver. If you put them too close together, they would interfere with each other. If you put them at an odd difference, it would work, but it wouldn't work well. So you wanted them at a one wavelength distance across this cable. And the way that you did it was you clamped a thing on there, and then you had a little drill, and you drilled a hole through the cable to get through the outer casing, the shield, and the dielectric in the middle to the center conductor. And then you had a part on top of that called the vampire tap that looked basically like a little needle, and you would stick it in that hole and it would go in and touch that center conductor. And then your transceiver would clamp onto that. And so your transceiver was a little box, probably about yay big. And then there was an AUI cable that went from there to the Ethernet card in your computer, and then your computer could be on the Ethernet. Oh man,
That was 10 megabits.
it was 10 megabits per second maximum. You could have a maximum of 100 stations on the network, and the cable could be no more than 500 meters long, and it had to have a terminator at both ends of the cable. Thin Ethernet was an adaptation of that used RG58 cable, and they called it 10 base 2 because the cable could only be 200 meters, really 185 meters long. The idea here was you could have a maximum of 30 stations on the physical network. It would do 10 megabits per second max, and each station had a little T connector. And so the cable would come in one end and go out the other end, usually had BNC connectors on it. And then it was a little T-shaped connector, and the T would hook directly onto the transceiver, which was either one of those little boxes, just like on ThickNet, or a lot of computers by that point had an Ethernet card with a BNC connector on it. You could attach that to it. The biggest problem that we ever had with ThinNet was somebody in their office wants to move their computer to the other side of the room. So they unplug the cable from the T, and that breaks the network for everybody because there's no terminator, right? And so hunting that down was always a challenge when somebody would do that. And you tell people in advance, just take the T off of your computer and leave the two cables with the T attached. It'll be fine. It won't break anything. But people being people, they don't do that. Anyway, the reason that there was a limit to 30 stations is that every place you had one of those T, the radio signal coming along that cable some of it would go down the T and some would continue down the wire. And so it would go down the T and bounce off and come down behind it. And so as you spread out more and more of those, you'd get that signal mixed up and you'd have too much noise by the time you had more than 30 stations. So ThinNet only allowed 30 stations. The next advancement was twisted pair Ethernet, which they called 10 base T, T for twisted pair. Twisted pair being the same kind of wire that you use for your telephone, basically. It would do 10 megabits per second, and it required some kind of hub or switch device, hubs initially, and then later switches that was centrally located. It was a star network, so one cable ran to each machine. You could have a maximum of 4 hubs on the system within a single collision domain and still have it work. So if you had like we had a lab where we had a single Ethernet drop into the lab, and we had a hub in there that all the machines in the lab were on, and that worked fine as long as nobody plugged another hub into that hub. If somebody plugged a second hub into that hub, you'd end up with too many hubs on the network in sequence, and it would break things. Things would just fail in weird, strange ways. There have been advancements with twisted pair Ethernet over the years. 10 base TX or 100 base TX would do 100 megabit per second. 10G base T or 1000 base TX to do a gigabit per second. 10G base T will do 10 gig per second, and up to 40G base T will do 40 gig per second on twisted pair lines, which is pretty freaking amazing to see that much traffic going through. I've also seen now a 2.5 gigabit per second interface type that people are using for different things. I don't know if that's a adaptation of the 1000 base T or an adaptation of the 10 gig T, or if it's a completely separate one in the middle.
We use a MUX that actually will transmit a terabit.
But you're using multiple connection points for that.
Well,
Yeah.
it's back.
Yeah.
The
Yeah.
2.5 gig is off the 1000 base T.
The
Yes,
one
iteration up to that, yeah.
is it okay? So yeah, so that's I mean the things that they've done with Twisted Pair are freaking amazing. And there's also fiber Ethernet, which is running Ethernet protocols over fiber. We talked briefly about FIDI as being a fiber token ring type network. Fiber Ethernet is basically running Ethernet protocols on glass with lasers, and your fiber can be up to 200 kilometers long and run up to 400 gigabits per second. It's amazing.
Way more than that. That's what I do for you.
More than that. So I know there's like InfiniBand and there's a few other technologies.
DM, which is dense wave multiplexing.
So there's
They
so
transmit each light fragment will transmit you can't even imagine. We have circuits that are 80 OC 192s per second.
On one fiber, multimode fiber, right?
88 OC 192s.
88,192 on one fiber, using multiple lasers, multi-axis fiber, right? So
It's not, it runs through a prism that breaks out into
into the different colors, yeah, different frequencies, yeah. Yeah. So glass is king, right? Fiber is definitely the king for speed.
You're using multiple fiber then for that stuff, right?
No.
Well, so one fiber will do that, right?
Multi-mode
That
fiber, not
nice.
single. So it uses multiple frequencies instead of just one.
Yeah.
frequency.
Yeah,
Yes, you're right.
multi-mode fiber, yeah.
Yeah.
So then, of course, there's RF networks, which take the wire out completely and allow you to just use radios on both ends and send the signal through the air. And that's what we use for Wi-Fi. Basically, Wi-Fi is an Ethernet protocol running on RF. And there's 2.4 gigahertz and 5.8 gigahertz. There's a 3.6 gigahertz band that's also been used. We don't have access to that anymore for whatever reason. Somebody waved too much money in the FCC's face and they decided to take that. Yeah, Verizon, right? So, but Wi-Fi is essentially Ethernet protocols running on RF signals. So it's pretty cool. And it can get, I think, what's the max for Wi-Fi? 600 meg or something like that. It's pretty good.
It's like 650 if conditions are perfect.
Yeah. So
That's why when you got 1 gigabyte fiber going in, and everybody else is on Wi-Fi, they don't get the
full benefit of it, right? So, all right. So let's talk about the IP.
1 meter.
Yeah.
That's speed.
And you have to have a dish antenna pointed. No. Yeah.
And it's like focused, like less than 6 inches.
So if you put your hand in there, it'll chop it.
Right.
So much.
All right. So let's talk about IP networking. So IP is short for the Internet Protocol, and it was developed for the ARPANET back in the 60s. The ARPANET was a precursor to the Internet. And we usually talk about Internet Protocol and the concept of TCP/IP. We always say, oh, it's TCP/IP, not necessarily using TCP, but that's the way we describe it. Okay. So we'll talk about what TCP and IP are and why they're different and that kind of thing in a sec. So the IP protocol is a 4-layered protocol stack. Okay. You've got the application layer at the top, which is the individual applications and the protocols that they're using. Then you've got the transport layer, which is typically TCP for connected sessions and UDP for unconnected sessions. And we'll talk about the difference in those in a minute. Then you've got the internet layer, the IP layer, and there are some other protocols that live at that layer as well. And then the link layer is the physical layer, and that incorporates the Ethernet, Wi-Fi, whatever the physical layer is for that, and the data link layer. Okay. So if we map that into the OSI model, this is how they line up, right? So you've got the IP side on the right, the link layer encompasses both the physical and data link layer in the ISO stack. The internet layer encompasses the network layer. The transport layer encompasses the transport layer. And the application layer encompasses the session, presentation, and application layers in the OSI model. So you can kind of see how it plugs into that OSI model. The OSI model still applies. Every network protocol can be shoved into this OSI model. It was designed for that. The IP layer kind of spreads that out a little bit and uses the pieces of it that it wants to use and that it needed to use. All right, so let's look at the anatomy of a packet. So everything on the wire is a packet. Everything that gets transmitted or received is a packet, right? It's a discrete chunk of information. And if you think about it, from the top down, as you move through those layers, each packet gets some things added to it so that that particular layer can do whatever it needs to do with it. Okay. So at the top layer, the application layer, in our example, we've got a header and a data for whatever this Modbus is. Okay. I'm not going to talk about Modbus because any protocol could be substituted in there, SMTP, HTTP, whatever you want, right? So there's some information that's associated with that packet of information that comes out of the application. When it gets to the transport layer being TCP in this case, then a TCP header is added to that. And that header includes certain flag bits that talk about what's going on in this packet, some correction codes, sequence number, various kinds of things that are needed for the TCP protocol to do its thing. We'll talk about what the TCP protocol does in a minute. That gets passed down to the internet layer where an IP header is attached to the front of it. The IP header contains the source and destination IP addresses. Okay. And then from there, it goes down to that data link layer. And in this case, we're talking about Ethernet. So an Ethernet header gets stuck on the front of that too. And the Ethernet also sticks a cyclic redundancy check code at the end of the packet so that it knows if the packet was transmitted correctly.
Well, that's the first place that takes place, is it that in there?
It could happen higher too. It depends. I mean, you might have some kind of encoding for that in your application. TCP definitely does some of that too, but there is a CRC associated at that physical Ethernet layer.
And you need to understand that this is all one.
This is all in one packet,
It
right?
encapsulates it.
Yeah, so if you're looking at a whole packet, you can peel off the headers as you work through the contents of the packet. Eventually you get to the payload itself, which is the data, right? So that's basically what a packet looks like as it goes out on the wire. When it starts at the application, it gets all this stuff tacked onto it. Then it goes out on the wire, gets to wherever it's going, and gets that stuff peeled off as it comes back up the stack to the application on the other machine. So pretty amazing all this stuff actually works when you get right down to it. All right. Let's talk about physical network addressing, okay? So Ethernet and Wi-Fi use the concept of a MAC address. MAC is a machine-specific identifier, okay? It's a 6-byte number, 6 octet. I always say 6-byte, but I shouldn't say that. I should say octet because some machines don't use 8-bit bytes, and that can confuse people. So if I say 6 octets, then you know I'm talking about an 8-bit number. An octet is an 8-bit number. So the MAC addresses are supposed to be globally unique. Typically, the first 3 octets define the manufacturer of the device. And then the last 3 are essentially a serial number of the device from that manufacturer. Okay. So whatever the first 3 are assigned by an organization. I think it's IEEE. And then the manufacturer can decide what goes in those last 3 bytes. The only rule being that it needs to be globally unique overall. Okay. Let's see. So these are called a UAA, uniquely assigned address. Some hardware does allow you to set the MAC address, and you may see that sometimes. If you've ever had one of those travel routers that you can take with you to a hotel and use it to connect to the Wi-Fi in the hotel, maybe the hotel only gives you one wireless connection, and you've got 6 devices that want to use it. Well, that device sits there and acts like a little router, and it has the ability to say, well, I'm going to clone the first device that connects to its MAC address and use that on the network side. And so it knows enough to separate the 2 of those out. But I've seen that on home routers as well. If the first time you plugged into your Comcast network, you used your computer, you want to keep the same IP address, you need to keep the same MAC address. And so you tell your router to clone the IP of your computer or the MAC address of your computer as it goes through. And so that's what can happen there. You can actually set that. You can spoof that. Okay. So keep in mind, that's not necessarily a secure thing. Okay.
MAC address, where people just buy a full hardware just to get the MAC addresses and resell.
Yeah. It is a limited resource, right? The 6 octets, 48 bits, it gives you 281 trillion addresses to work with. There's a new version of MAC that's coming out that will use 8 octets, which gives you 64 bits. And 64 bits will give you probably enough MAC addresses for every atom in the universe to have a MAC address. Well, at least every atom in the solar system. But yeah, so 64 bits is a big number. But we'll see when that rolls out because that's going to confuse some things as it starts rolling out. Systems will need to be smart enough to handle both for quite a while as they do the transition. All right. So let's talk about IP addressing. There are 2 versions of IP addressing or internet protocol in use on the internet today. There's IPv4 and IPv6. IPv4 was the original system. The IP addresses are 4 octets long or 32 bits. If you look at an IP address and it's like 20.219.18.7, that's an IPv4 address. Okay. The problem is 32 bits only gives you 4 billion total nodes. And the way that it's divided up, we'll talk about how it's divided up in a minute, but the way it's divided up, we've actually been running out. In fact, we're actually completely out at this point. Different organizations own blocks of addresses, blocks of address space. And so there's a lot of juggling and reselling of address space that happens among the big players. But yeah, there is actually, every block is assigned at this stage. Dan, you had a comment.
As of 2023, there are 3.4 billion IPv4 addresses assigned. So there's a maximum of almost 4.3 billion you can do. IPv6.
We'll talk about IPv6. So IPv6 is the new system that was originally described or decided on in 1998. It uses 16 octets per address, which is 128 bits, twice as many bits as the new MAC addresses are going to use. You will have enough IPv6 addresses for every atom in the universe, and probably for every subatomic particle in the universe when you get everything added up.
There,
Dan.
there are 340 undecillion IP addresses in IPv6, and undecillion 340, and then 36 zeros.
Yeah,
On the
there's a
other
lot.
side of the 340.
There's a lot. Let's put it that way.
It's hard enough
And you don't
to.
need those because when corporations, like you say, they buy up blocks of addresses, don't actually use.
You don't use the whole block, right?
They take one IP address and create, a whole.
Yeah, we'll talk about that.
It's hard enough.
How that happens.
A
Right? Yeah.
IP address, I don't know.
That's why we have the domain naming system so that you don't have to remember the IP addresses, right? I don't really talk about DNS in this presentation. I really should have put in a slide about DNS. We'll see if we can fit it in somewhere and we'll talk about it. So AREDN mesh networking only supports IPv4. It does not support v6. So we're going to concentrate on IPv4 for this presentation, but I do have a slide later where we talk about some IPv6 specifics. So when we get to that point, we'll dig back into IPv6. But for now, we're going to concentrate on IPv4. Okay, so IP address for IPv4, remember, is 4 octets long. It's a 32-bit number. It's usually represented as what we call a dotted quad. In this example, 166.70.240.201. Each of those numbers can be from 0 to 255. If you ever see, like, you're watching a show or something and they're like doing a trace route and the first octet is like 327, you know that's fake because that number can't be bigger than 255. So you know they've just made that up, which is fine. They need to do that. The 32-bit number is divided into 2 parts, a network part and a host part. The hosts where all the bits are 0 are reserved and can't be used, and the ones where all the bits are 1 are reserved and can't be used. Okay, they have special purposes. All zeros in the host part is a definition value for the network itself, and all ones is the broadcast address. We'll talk about broadcast in a minute.
And we're only talking about natural class IP addresses.
We're going to talk about that a little bit too. So originally the network space was divided into classes. You had class A networks, class B networks, and class C networks. Class A networks carved off 8 bits of the 32 bits for the network part, and the other 24 bits were for the host part. So that gave you 16 million hosts on your network. Now, and only 126 of these networks were available in the entire internet. Okay. So you can think about that. How many organizations actually need a class A network? How many organizations are going to have 16 million hosts on their network? I know AT&T's got one. I know like BBN's got one. There's a few different companies that got those back in the day. Okay. Class B networks use 16 bits for the network part and 16 bits for the host part. So each network could have 65,000 hosts, and there were 16,000 networks available in this class B. A lot of universities got these class B addresses. A lot of medium or big companies got these class B networks back in the day. And then class C networks used 24 bits for the network and only 8 bits for the host part. That limited you to 254 hosts. Now you're thinking, wait, shouldn't it be 256? There's 8 bits, right? But remember, all zeros is the network, all ones is the broadcast. So those two addresses can't be used by a host. So that leaves you 254 hosts on that network. And there's 2 million and change class C networks available. Now, there were also class D and class E networks that were for special purposes. The class D networks, which had the first octet from 224 to 239, are used only for multicast networking. The class E networks, which had the first octet being 240 to 255, were reserved for experimental use. Obviously, this network division model didn't scale, right? This worked great in the 70s and even the 80s. But as we started to get into 90s, we started to realize that more and more people wanted to be on the internet, and this wasn't going to work. So a new model was developed in the mid 80s called variable length subnet masks. And they use a thing called CIDR, classless interdomain routing, to make this work. The basic idea is you take your IP address and you chunk off however many bits you want for the network part and for the host part. So in my example here, I have network 1.2.64.0/18. So that says for this particular network, 18 bits are going to be the network part, and the rest of them are going to be the host part. So in this case, the broadcast address would be 1.2.127.255. Remember, all ones in the host part. And host could be anywhere from 1.2.64.1 to 1.2.127.254. Okay, you see how that works? Oh, yes.
Easiest way it was described to me, which totally made sense afterwards, but your subnet mask decides what part of the pie
Is right. The subnet mask defines. I'm going to pull up an application that I wrote. Let me see if I can grab this.
you give a 10 megabit pipe, your subnet mask tells you how much of that pipe you're allowed to use.
You know, it might be worth just showing how those bits are calculated, where the 4 octets, you know.
Yeah. So I wrote this program to help me understand what was what and what went where, right? So let's use our sample network 1.2.64.0. And then, so this was originally a class A network because the one over here meant that it fit in that class A section. But we're going to subnet that down to 18 subnet bits. And so my subnet mask is going to be 255.192.0. And you can see that in hex over here, FFFF C000. So the subnet mask is basically all of these are ones and the host part is the zeros, right? So that's how this actually comes about, the subnet mask. Don't worry about the Cisco mask. Nobody uses that anymore. But the concept was when you did this, you got 1,024 subnets of this particular class A network. and 16,382 hosts per net with your /A team. And this is the list of all of the subnets in that range. So there's 1,024 lines here, one for each subnet. And the one in particular that we're talking about is 1.2.64.0. And so his broadcast address would be 1.2.127.255. And the valid host could go from 1.2.64.1 to 1.2.127.254. Now, since we don't use the classes anymore, this tool is kind of out of date, but you can just drag this down to wherever you want the slash to be. So this would be the /18 CIDR with no subnets of that. If I was to purchase a /18 from my network provider, I personally could subnet that even further and get multiple networks within my network, right? So I have that ability. And a lot of your ISPs will do that. They'll have acquired a block of addresses, say they've acquired a /20, and they will give each person a /30 network with 2 hosts per net, one being the router port and one being the client's port. So every network only has 2 hosts on it. And so they would be able to do that for 1,024 subnets with their /20 network that they bought, right? So kind of a fun little application. It's really terrible. Don't look at my code. I wrote it years and years and years ago, and it reflects
So
my.
explain what a broadcast is.
Okay, so the broadcast address, when you send out a packet on the network, you normally know where you want it to go. You want it to go to a particular other machine, right? So you're going to put in the destination IP address of the machine you want it to go to. Now, if you don't know which machine you want it to go to, you want it to go to every machine on the network, you're going to send it to the broadcast address. And that's the address with all ones for the host part. And so every machine will see that packet. And that packet will come farther up in the network stack past the IP layer. It won't be dropped because it's not specific to that machine. The machine will go ahead and process it. So that's AREDN's a different ball of wax. We'll talk about that in a bit. No, you're good. You're good. So the concept also is there's this thing called multicast. Remember, we briefly talked about Class D networks, which were multicast networks. And the idea there is that you could register your interest or membership in a particular multicast group, and then those packets would be received by your machine as well as all the other machines that are members of that multicast group. Okay. And then when you're no longer interested in receiving those, you would deregister and your machine wouldn't see those packets anymore. So multicast was a great concept that was amazing when they started talking about sending live video and stuff over the internet, but it hasn't really done it. We haven't really done anything with it because everybody has this concept of, well, if I'm watching the stream, I want to be able to pause it and start and stop it when I want to, and I don't care about the other people. So, there's no cooperation on the internet today in regards to that. So multicast is something that is still kind of experimental at this point. We'll talk a little more about that when we get into the IPv6 discussion, but essentially, multicast is one of those features that came about before there was a good use for it, and unfortunately, the internet moved on with nobody really adopting it. So, one of those things. All right, so there are some special IP networks. Some IP networks have been assigned or given special meaning. The network 0 or 0000/8 refers to the current network. So you can always use 0000 to refer to the network that you're currently on. I don't know of anybody who does this, but the protocol says this is the local network, okay? 127.0.0.0/8 refers to the local network within a given node or a given host, okay? So you can use the full network stack and all the network protocols and everything, even if your client and server are both running on the same machine, And if you do it on this local network, this 127.0.0.0, and typically your machine will be 127.0.0.1 on that network, but it doesn't matter what IP you use because it's local to your machine. So that whole Class A, that whole entire Class A network was reserved for use on everybody's individual machine, not to ever talk to anybody outside of the machine. Okay? Yes.
Does that mean if I have my own self-hosted Wi-Fi and I'm trying to tell someone, join it, or they join the Wi-Fi, so they're on the network, that I could give them the 0.0.0.0.8 as their host, and they would, and I give that to index?
No. Not if they want to be able to talk to anything outside that network. Right?
But say it's a self-hosted network. And they're out in the wilderness, and they don't need to talk to anybody else with that.
I don't know. That would be interesting to try. I would recommend using one of the reserved networks for local networking. Other than that, we'll talk about those in a minute.
The 127.
The 127 you can't.
Then I basically have to tell them, I have to look at the computer and say, okay, this is the one that is assigned.
Yes.
So
And you would still need to do that. You could conceivably give them 0, but unless your applications are listening on 0, which they may or may not be, they may be listening on a wildcard, in which case it might work. I don't know. I've never tried it. Like I said, nobody that I know of actually uses network 0, but it would be an interesting experiment to try it out and see what happens when you do that.
Is that a gateway?
You wouldn't need a gateway anyway if everything was on the local network. So it wouldn't eliminate a gateway.
You wouldn't need a gateway or anything like that if it's all local, if it's the same network.
Yeah, so 127 is local to the host. 192.0.0.0/24 is reserved for the IETF for transitioning from IPv4 to IPv6. IETF is the Internet Engineering Task Force, and that's the people who actually define what these protocols are that are out there, okay, on the internet. So they basically run the internet. There's also 192.0.20/24. That's
Explain what /24 is /8.
so we talked about that in the previous slide, right? Where that's the CIDR part. It basically says 24 bits of this number are the network and the other 8 are the host. Okay. So on the /8, 8 bits are the network and 24 bits are the host out of our 32-bit IP address. See you, Dave. Thanks for coming.
You forgot to take the CCNA test.
Does that explain what I'm talking about with the /8 and /24? Or not really?
I'm sorry?
Does that explain the /24 and the /8? This is the CIDR, the classless interdomain routing thing.
I was hoping that there would be some diagram that showed what that really looks like.
Yeah, I don't have one.
That's okay.
I don't have one, so
People who deal with this every day, we think everybody knows about it.
yes,
right?
that's
So
very
it's-
true. Very
it's-
true.
Yeah.
So this 192.0.20 is defined as testnet 1, and it's mainly intended to be used for documentation purposes. So if you're writing a document where you're saying, now set your network to this, in your document, you can use this network and be sure that nobody else is going to be using this out on the internet. Okay. So you don't want to use your real IP address because somebody might start sending you traffic if you do that. You don't necessarily want that. So some of these test nets, there's 3 of them that are out there, and they will be used for documentation purposes. 192.88.99.0/24 was reserved. It was originally used for IPv6 to IPv4 relay. Remember, the 192 was used for transitioning from IPv4 to v6. This is for v6 to v4 mapping. And then 192.88.99.0, that's the same address. I don't know. That probably shouldn't be the same address. It's used for benchmark testing between subnets. One of those is wrong. So just pretend those aren't there. 192, 198.51.100.0 is another test net. 203.0.113.0 is another test net. And then 233.252.00/24 is the multicast test net. So remember we talked about multicast a few minutes ago. That would have been the test net for your documentation purposes for multicast stuff. 224/4 is reserved for future use. That was the class E that we talked about before. Okay. /4, we haven't gotten to /4. Basically, your class A was a /8, right? Half of that brings you all the way to class 4. And so those networks were all reserved in this class E. Okay. And then 255, 255, 255, 255/32, no host part, all network, was reserved for limited broadcast destination. Okay. As far as what that means, I couldn't tell you. In addition, there were 3 networks that were defined for private use, primarily in disconnected or NAT applications. And this is where your disconnected net would probably fit in. And they are 10.0.0.0/8, which is a full class A, so 16 million hosts, right? 172.16.00/12. It's not, remember, a class C would be a /16. So it's like 4 bits of class B would be /16. It's like 4 bits of class B network. So what is that? 4 bits is, how many is 4 bits? 16? Yeah, so 16 class B networks essentially are out there for this 172 network. And then 192.168.00/16. So 255 class C networks are reserved for these type of applications. You've probably seen 192.168.0 before on your home routing equipment. Most often your home router is going to be using NAT and it's going to use one of these subnets. My Asus network router wants to use 192.168.50, but you'll have to see 192.168.0, 192.168.1, and then whatever you've got for your host part at home. Yes.
So
yeah.
basically, any private network, so 10, 172.16, and 192.168, they are unroutable.
They are not
You-
routable
you
on the
cannot-
internet.
Cannot send a destination IP address to 192.168.13.12 across. It cannot leave your house.
Unless you've got some kind of a tunnel VPN or something like that that allows you to
When you're
adapt
talking
like that.
to another private
We'll
network.
talk about that in a minute, but
So you use that for local internet.
you would use that for your LAN, right? And AREDN uses net 10. So with AREDN, basically it's one flat network and each machine uses its MAC address to figure out what the last 3 octets of its IP address should be on net 10. And so that's how AREDN decides what its IP is going to be. So when you first boot up your new AREDN node and you're looking at the setup screen and it says, oh, by the way, your address is going to be this when it reboots, it's because it's calculated that based on the MAC address of the host of the machine itself. Okay.
What happens when it keeps changing?
Shouldn't.
It shouldn't. It should never change.
It should never change, either on the LAN or the WAN side. It should
Yeah.
never change.
Well, the LAN side might change if you change the size of the LAN. We'll talk about that when we get to
That's
data.
That's what we saw changing.
Yeah. We'll talk about that on when we get to the AREDN part. Yes.
Yeah.
Maybe this belongs in the area part too, but I'm just wondering if, a lot of times if you're programming some sort of server response or form type response, you say, get the address server and, you know, you get JavaScript or PHP or something, there's a way to do that. How does AREDN do that? Because I've seen how it shows up, it's like local.mesh.
Oh, DNS.
Yeah. DNS is the secret for that. I don't have a slide for DNS, but I'll feed it in here as we get through into some of the protocols.
So that's why all of my AREDN stuff start with 10. I can just.
Yes. All your AREDN stuff is going to start with 10, right? Okay. So we'll talk more about how AREDN uses net 10 when we get to that part. There's also 44 net. which is 44.0.0.0/9. It's not the full class A. It's subnetted down 1 bit from the class A, and 44.128.0.0/10. So it's like one and like 3/4 of a /A, essentially, is what we're getting here. This is AmperNet, the amateur radio. I don't remember what Amper stands for, but this is a network that was specifically designed. Originally, it was the entire class A of 44/8, but they've cut it down. They've resold a quarter of that network. So it's currently managed by the ARDC, the Amateur Radio Digital Coalition, I think. Conference. I don't know. It's associated with amper.org. It's been used by amateur radio operators since the 80s for various purposes, and you can get a 44 net subnet from them if you want one. So if you want to do some stuff on 44 net, you can get that. You can attach to other 44 net nodes over the internet using tunneling, or there's other mechanisms as well. So you can get a 44 net address if you want one, if you want to play around with that. I haven't done it, but it's kind of cool. Probably will do it at some point just to add it to my toolkit of things that I've done. Okay. So that addressing happens at that IP layer, that internet layer. Okay. So there's other things that live at the internet layer. The internet layer is basically for managing the internet itself. All right. And one of the concepts that was part of the development or design of IP was it wanted to be a self-healing network. It wanted to be able, it was designed for the military. And the goal was, well, what happens if they take out one of these sites? We still want these other sites to be able to talk to each other. So they need to be able to route around a failed setup, right? So there are different protocols that are used for the network itself to decide what's what, what's where, what's broken, what's not broken. Okay. And out of these are ICMP, which is probably one that you've used before if you've ever run the ping program. Ping will send an ICMP packet to another host, and it will receive an ICMP response back saying how long it took to make the round trip, usually in milliseconds. And so you'll be able to see, yes, I can reach that guy, and it took this long to get back and forth between them.
How does it know?
That happens at the routing. Okay, we'll talk about the routing.
Okay. That's always been a mystery to me. How does it know?
Yeah, it's magic.
How does it know that?
There's a few different ways that it knows, but we'll dig into that in a minute.
Thermos bottle keeps hot things hot. And
Yeah.
things cold.
How does it know which is which? Yeah, right. Yeah. Okay. IGMP is Internet Group Management Protocol. Remember, we talked about the multicast groups. IGMP is the protocol that is used to add yourself to a group or remove yourself from a group. So it registers that you are interested in a particular multicast group or no longer interested in that multicast group. There's the ARP protocol, or the address resolution protocol, which handles the mapping between the IP addresses and those MAC addresses on that lower level. Okay, remember we had IP at this level and we have Ethernet down here, and Ethernet is using MAC addresses. IP is using IP addresses. So there has to be some way to map in between the two of those. And that's done using ARP. And then there's also reverse ARP, or RARP, which allows a host that knows a MAC address to find out what the IP is for that address. So it's basically the reverse. The ARP protocol says, I have an IP address. What's the MAC address for that? And then the RARP protocol says, I have a MAC address. What's the IP address for that? Now, RARP is, you won't see that too much on the wire, but you'll see ARP all the time. And each node will maintain a list of an ARP mapping, and it will use those to look up what it's found out so far. That table is usually of a certain size, and so things that are most recently used will expire from that table. So you might have to ask for them again. But you'll see that on the wire, you'll see a ARP who has packet go by, and it'll include an IP address in it. And then whoever knows who that IP's MAC is will respond back with, oh, it's this. Okay. So in the context of routing, remember my IP network might be this, and this guy's IP network might be something else. There's tons of stuff in between. My physical Ethernet's not connected to his physical Ethernet. So how does it get over there? Right? This is where the routing comes in. So when I say, hey, I've got 1.2.3.4, who has that? My router is going to say, oh, I know how to take care of that for you. Just send it to me, and it'll give me its MAC address. So when my packet hits the wire, my router will receive it, and it lives at a higher level. So there's this layer one, there's this layer two, and then there's this layer three level that the IP layer is living at in the OSI model, the layer three level. And the router is running at that level. And so it will look at that and it'll say, oh, this IP address, well, I don't know how to get to that IP address myself, but I have a default route that says go to this guy. So I'm just going to send it to that guy and let him worry about it. And so he sends it on to that guy. And that guy will either have a default route of his own or a routing table of networks that he knows about that he can look up and see who the next neighbor is and decide who to send it to, who he's directly connected to that he needs to send it to. And there's a whole protocol called BGP or Border Gateway Protocol, which is used to shovel information around the internet about who's connected to what. Okay. And each physical island network has an ASIN or an identifying number that says what it is in BGP and who its neighbors are. And so this information goes out into these like main core routers, and they will know, oh, well, if I get a packet for this guy, 1.2.3.4, well, I know where 1.2 is. I'll just hand it over to that guy. And so it sends it on to the next node and it percolates through the network. If you've ever run a traceroute command, you'll see this happening in real time as you do that. In fact, we can go ahead and bring that up while we're talking about it. Let me get a terminal here. I'm going to go ahead and make this a little bit bigger so people can see it. Whoop, maybe I will. Where did it go? Let's see. No, that's not what I wanted. Let me just see if I can get. Huh. How about if I do this? Let me get a new window. Okay. Let me bring this up. Make that a little bit bigger. And I'm going to run a trace route to
BASH $sign mean?
so the shell that I use is bash. And so bash is just an indicator for me that I'm in the bash shell. And the $sign says that I'm logged in as myself. If I was to run sudo and put in my password, then you see it changes to a £. And now it says that I'm running as root. I don't need to do this as root, so I'm not going to do that. But yeah, so I'm not going to do that. But all right, so you'll see in my prompt here, I have my username, JLP at Heptagon is the name of this computer. And then this number is the history number of my commands. So like if I was to do an LS here, now you notice it's 1472 instead of 1471. So I can actually say, well, I want to repeat the command that I ran for 1470. I can just do that and it will run that sudo command again.
Where does it keep that?
It keeps it in a list. If I run history, it'll print out the whole list.
Static list, it stays somewhere.
It adds to it as I run commands. So, and it rotates off.
It's a hidden file.
Yeah, it's basically in a file called .bash history. So, but we'd have to go into a whole Linux class to talk about that kind of stuff. So, but yeah, so you can get the idea. So I'm going to run a trace route to www.google.com. We'll see how long it takes to get there. Oh, trace route not found. I'm not going to run a trace route.
Trace RT.
Nah, no, this is not a Windows machine. I'm going to use MTR instead. So MPR is more dynamic anyway. It'll look cooler. So um, basically, what's happening here is I'm going to send packets from my machine, which is 192.168.1.125. So the fire station is using 192.168.1.0, right? And I'm going to Google, which is at 172.217.7, 320. And then that's not 320, it's got to be 32. And then this, let me see if I can make this a little wider. There we go. Now you can actually see it. Okay, so you can see the timestamp over here that's changing. And what it's showing here is when I send a packet to Google, this is how it gets there. So the first thing it hits is this guy called underscore gateway, whoever he is. He's something that's local here in the fire department. Okay. And then from there, it goes to this 69.162.228.1. And then from there, it goes to 69.162.234.191. And then it hits level 3 and it hits this machine AE60 bar 1, Salt Lake City 1 on level 3.net. Then it goes through these three guys. And finally, it gets to SLC 18 SO3 in F4 .1E100, which is a Google owned network. Google, the Google number, not Google, but Google, is 1 followed by 100 zeros. So they use 1E100 to represent that in their naming for their reverse names. And so they've actually apparently got a POP or a point of presence here in Salt Lake on some routing group that's here in Salt Lake that speeds this up, right?
Right.
So I hit them almost directly. And so you can see over here how many packets are lost as I'm sending them through. Some of them don't come back. And it's not because they're like there's a problem with them. It's probably because these machines are too busy to respond, or they just don't bother to respond to me for every packet. But you can see how many I've sent. And then this shows the ping time or the number of milliseconds it took to get the response back. So the average response back from Google is 4.8 milliseconds because I'm hitting that local Salt Lake Google guy. Let's try something a little bit different. Let's go to, let's try Yahoo. Anybody still use Yahoo? So here you can see a couple of these guys. Those guys are still really slow getting back to me. And it hits into HeliumNet, he.net, and then it goes on to CoreSite, and then it goes into Yahoo. And Yahoo's their internal stuff is there, but it's not actually responding to me. So this will never come back. But you can see I'm getting 13.7 milliseconds back and forth to www.yahoo.com. If we go to something weird like let's
Go to the Oregon Mesh site.
all right. We'll see what happens there. See, that's hosted fairly by Fastly. So it's pretty close. Let's pick on something like MikroTik.
Oh, yeah, that should be somewhere near.
So if I go to MikroTik, we'll see where we end up with that. Again, we're only getting out 10 hops, but it is in
address.
It is in Germany because it's hidden Frankfurt here over here on level 3's network.
Actually, it's in Latvia.
Yep, it probably is. Yeah, by the time it gets through these three hosts that aren't responding. But I'm seeing 150 millisecond round trip time, which is pretty darn good for getting to the other side of the planet. I don't know any Russian hosts, Dan. Do you have one in mind that you want me to try?
Try nhk.jp.
nhk.jp.
That's the Japanese state broadcaster.
All right. So there it took 12 hops to get.
And they're hosted in AWS. So.
Okay. So it's just going into AWS somewhere, and AWS is hiding the routing from there. But I'm getting 13 milliseconds for that. Yeah, I don't know. The network has changed a lot over the years. It used to be you would routinely get, 15, 20 hops getting out to Australia or, Japan or something like that. Nowadays, it's like everything is much closer because they've tried to move the endpoints as close to the people as possible.
Right, and where you get something like Cloudflare that's in the middle, that's
Yeah,
blowing it.
that's hiding that from you. Now there's something you don't see too often. There's a net 10 in the middle there. Where did he come from? Somewhere in China. And a 192.168 before we finally hit back to a routable IP address over here. So there's
The
some
Valve radio.
there's some weird stuff happening in China over there. So
Could that use a very firewall?
it could be, it could be. Okay, so let's get back into our presentation.
That was a scroll.
How do we get back to current slide? Okay, there we go. All right, so does that answer your question about how the routing actually works and how it gets from my machine to wherever it needs to get to? Okay. All right, so let's talk about what's happening below the IP layer. So the physical and data link layers, or the network layer and the IP stack, is below IP. And that's how bits get put on and taken off of the wire. So things like the Ethernet, fiber, Wi-Fi, those all live at that layer. And some of the interesting protocols that live down there are STP, or spanning tree protocol, and VLAN tagging. What spanning tree protocol does is, remember we were talking about the concept of a hub and how it looks like one long single wire logically, and how a repeater looks like two separate wires with a little box in between, but this is happening at the layer 2 level. So switches operate at this layer 2 level. So they only work with the MAC address. They only work with the Ethernet part of the packet. And what switches do, when you plug a new thing into the switch, it immediately starts by sending everything it's got down that wire until it hears something from that wire with a particular MAC address on it. And once it hears that come back, then it says, oh, that's the MAC that's on that wire. So I only need to send stuff to that MAC down that wire. So switches are really good about this, hiding that information from the other wires on the switch, right? And it's great because then you can end up with
the dumb switch, right?
this is just a regular switch, yeah.
Dumb switch.
Now, there are some switches that you can actually control them, and you can tell them, oh no, I want to see all your traffic all the time, and you put it into a promiscuous mode where you can see everything coming by. That's not the normal case of operations for switches. What happens if you plug a wire from one switch port into another switch port? Bad things happen. Okay. And this is where the spanning tree protocol appears, because it can say, oh, hey, I'm seeing the same MACs on both ends of these two wires. One of them is a loop. I'm going to get rid of that one. I'm going to turn that off. And so it turns that off, and it makes the network actually continue to function. Dan.
Years ago, I went to Las Vegas during, one of the Las Vegas. I had a class with Radiant Perlman, who wrote
The spanning tree protocol.
that. Was a very
good stuff.
Class.
Yeah, good stuff.
She told us how she developed that.
Yeah.
Brainiacs.
Brilliance. It really was. It's like just a great addition to switches, and made them a lot more robust in the face of people doing dumb things, which people will always do dumb things. So, you've got to expect that especially when you're talking with consumer grade networking gear or stuff where people can touch the ports. If humans can touch it, it's probably going to get broken at some point, right? So especially if soldiers can touch it, then it's definitely going to get broken, or firefighters, according to the fire chief. But all right, VLAN tagging, VLAN tagging. We'll talk about more as we get into the AREDN stuff, but basically what it is VLANs are virtual LANs, virtual local area networks. And the concept is you add another field to each Ethernet packet that says which VLAN it's on. And so it essentially, instead of giving you one logical network, you can have as many as you want, up to 4096 usually. In reality, your hardware probably can handle 32 to 64 of them without breaking down. But the size of the bit field allows you to have like 4096. We'll talk more about that in a minute. So that's what's happening below IP, right? So what about above IP? So we have the transport layer. And the two main transport protocols that make the internet work are TCP and UDP. Okay. TCP is the transmission control protocol. UDP is the user datagram protocol. We'll talk about UDP first because it's the easiest. It's a very simple protocol. It's easy to implement. It does not offer guaranteed delivery. So if I send a UDP packet to you, maybe you get it, maybe you don't. I'll never know unless you come back and tell me, hey, I got it. Then I'll know. Okay. Why do we use that? Because it's easy, it's fast, it's small, it doesn't need a lot of thinking to go into it. So for certain things that we want to do, we care less about did it get there than we care about did it get there fast. Okay. So it's not reliable. It doesn't ensure that your packets arrive. It definitely doesn't ensure that they arrive in order. We use it because it's easy and it's very lightweight. And it's not secure, but you can implement those things on top of UDP at the application layer.
It can be.
Okay. So you can do some things at the application layer where if I sent this packet to you and I never got a response back, I'm going to resend it, even though it was a UDP packet. That's being decided on at the application layer, not at the transport layer. Okay. So let's look at some sample UDP protocols. We've got the Echo protocol. Basically, if I send you a Echo UDP packet, you're just going to turn around and send it right back to me. Okay. Discard. If I send you a packet, you're just going to throw it away. Daytime. If I ask you for a packet, it will contain the current time of day. Now, a lot of these services used to be running on every machine on the internet all the time. A lot of them are not running anymore because people don't want just random user poking at their machine and making it do work without, being associated with them or whatever. But some of these will still work. So CareGen, if I send you a packet, you send me back a packet full of characters, just
It's
random
8
characters.
o'clock. I don't think we can discuss every single
Okay. Well,
protocol.
there's a bunch of them. Okay. You guys mind sticking around for another half hour? I've probably got another half hour worth of slides.
I'm good.
Uh, oh, Paul suggested pinging X-Mission. Sorry, Paul, too late. We're moving on. Okay. So how do you find a list of these protocols? There's a file called Etsy services. There's a corresponding file on Windows machines, but I have no idea where they stick it. It's probably in Win32 /Etsy /services or something like that. I don't know. But the services are identified by a port number, and the server will receive the incoming traffic, and a client will send packets. So a particular machine could be a client or a server, depending on what it's doing. Okay. TCP or Transmission Control Protocol, it does provide guaranteed in order delivery of packets, no duplicates. You'll get the packets out in the order that they were put in from the application layer.
So it puts them in a queue and it gets an acknowledgement.
TCP will
how it works.
TCP will automatically request retransmissions of packets that didn't make it. It'll maintain this connected status. So you'll either know that it got there or you'll know that it didn't get there.
Well, but how does it know that?
So there's a field that has a number on it.
A sequence
It is
number.
a sequence number. And if you get a sequence number 5 and the next packet you receive is a 10, he knows he did not get 6 through 9.
So he can
Okay, so
request
will
that those
request
be
to
retransmitted.
resend that.
Okay.
And that happens at the protocol layer, not the application never knows that's happening.
Right.
Okay. So the goal of this is for the application, I have a pipe or a tube from me to the server application on the other end. I don't care what's in between. I don't want to know what's in between. All I care about is what I put in this tube at this end comes out the tube at that end in the order that I put it in. And, it'll either get there in order or I'll know that it didn't. I'll get some message back saying, sorry, your connection failed or your connection was lost. And so that will happen sometimes, right? Your connection could get lost. You'll get an error that tells you that it didn't make it. So we use TCP for anything that's connection related. You open a connection, you shovel some data through it. Maybe you get some responses back. Maybe you shovel stuff back and forth for a while. And then when you're done, you close it down.
There's a way for an acknowledgement for every packet before it sends a new one.
Sometimes.
Yeah. The best analogy you can use for building the TCP connection, it's called a SYN-ACK is how it makes the actual connection. I use TCP's initial connection is like FT8. It's that, think of that exchange and think of UDP as like Whisper.
Yeah, UDP is just spewing it out
It's
there.
just spewing out like Whisper, where TCP is like FT8. There's an exchange.
So there is a rotating window of length that can be used, and it will automatically adapt to the conditions of the underlying network to grow or shrink that window as needed. So that if it's finding, well, shoot, I'm getting big chunks where I'm missing data and having to request retransmits, I'll shrink my window down so that my back and forth time is more frequent so that I know sooner if I've missed a packet.
Every packet that's said, it sends an acknowledgement back and then it sends
Yes.
the next packet.
Yes.
Okay.
It can send multiple packets before it gets any acknowledgements back.
Okay.
But there is an acknowledgement for each packet sent. Okay. And so both ends will know if they have been successful in sending that packet. And that's how your application will know that, hey, I've lost the connection. I've been sending packets to this guy. I'm not getting any acknowledgements back. I can't guarantee that the connection is going through. My buffer is full. I can't put any more in here without losing it. So I'm going to tell you I failed. And you're going to know that the connection has failed. Okay. TCP services are also identified by a port number. The server is listening on a port and accepts those connection requests as it comes in, and then it can send and receive through that channel. And then both sides have to close the connection when they're done. Okay. So you can have a half open TCP connection where I'm done sending and I've closed my side, but the server may still send some things back to me. And so I kind of have to wait until he closes his end to report back to the application layer, hey, this connection is closed. And this is all the rest of the data that I got, right?
So what's a great application for TCP about voice over IP? Can you imagine using UDP on VoIP calls? Right?
Actually, they do use UDP on voice calls.
Yeah. You're,
Now,
the logic behind it is you want the packets to arrive in a certain order.
yes,
Right? So it is important that.
but that's happening typically at a higher in the application.
Is
Yes.
there a standardized method that uses the same protocol, but that envisions a scenario of extremely long latency or just no response, but still?
So we, believe it or not, we use IP networking in space between Earth and space probes, where the transit time might be 20 minutes or several hours. And IP can adapt to that and work in that kind of an environment. So yes, we do that using IP. And there are protocols that are used specifically on those types of networks that take advantage of some of those restrictions and delivery delays and things like that. So we do that on what we call very high latency connections. And you'll see that the NASA runs the Deep Space Network, which actually does this kind of
I
stuff.
think about Voyager 15 million.
Yeah, Voyager is out there, man. It's
And
doing
it's
stuff.
flying.
And we're still talking to it.
pretty close to the home. You can go to a Walmart, you go to gas stations, you have the dish on there. They're talking to a satellite, right? So all the Walmart places are talking to a 30-meter dish in Bentonville, okay? And it takes every Walmart has the equipment that accounts for an 8-second round trip for a connection, right? And so you don't use a typical layer 2 switch to
Right.
try to talk to
Your
Walmart.
your protocol understands the nature of the latency that's
Yeah.
involved, and it does the right thing, right? So
It's engineered at the layer.
Yeah.
You're just not using off the shelf equipment.
yeah.
Right.
All right, so TCP protocols, there's a whole grundle of them. We're not going to talk about every one of them, but some key ones that I want to mention. Telnet is a remote terminal protocol. So if I open a Telnet connection to a machine, then I get like a virtual console terminal on that machine, and things I type can run commands on that machine and it can send responses back to me. Telnet does not do any encryption, so it's great for AREDN networking where we're not allowed to use encryption. We don't use it much on the big internet anymore. You may see it used for some internet bulletin board systems, and there were some games that used it. MUDs typically used Telnet to connect to them, things like that. But we don't generally do that too much anymore. We now use SSH most often on the internet for that kind of remote terminal protocol. There's SMTP, which is Simple Mail Transfer Protocol. That's how email moves around the internet. Okay. The domain protocol is the DNS. And I think you guys were talking about that out of band.
Yeah.
So
yeah.
This is basically the system that handles the mapping of host names and network names to the actual IP address.
And a quick question related to this. I know they have like, a monitor that you can plug into and remote administer, and you can administer keyboards and, I think even, USB devices. Are those the same IP as everything else, like ID?
It's all running on top of IP. So there's an application layer protocol that's handling the muxing of that data back and forth. There's several different protocols that do that. AREDN can handle that. Yeah, absolutely. You can do remote console stuff on AREDN.
Yeah,
That's
if
fine.
if you were reading the thread about Jan talking about the video cameras
Yeah.
going back and forth, same principle.
Yeah, well, and I also wondered about some of these USB devices. In theory, you could control a USB device.
You could. Yeah, in fact, there's a protocol that I use called No Machine that does virtual console, and I use it to connect to my Raspberry Pi computers all the time because it gives me a view of the console of the machine on my laptop here, wherever I happen to be. I don't have to be at home for that. I can map through VPN. I can get into my network and do that. The idea being that I not only have the video, I have the keyboard, I have the mouse, I can attach and detach devices. I can print through that. I can do audio through that connection. All kinds of stuff can happen over that.
Is that so
Connection.
for remote control of HF stations, for example?
They use a different protocol, but it's a similar concept.
Okay.
Is it automatically encrypted?
It doesn't have to be.
It depends on the program.
You can turn that encryption on and off. Dan.
Something, just a fun fact. My life is network management, and I deal with sites, typically DoD sites, that we do SNMP over TCP.
Yeah.
For various reasons, but
Yeah, so some of these protocols you'll see on both the UDP side and the TCP side. Domain is one of those. Most of the time, you want to look up an IP address for a host name. That's the only thing you're asking. It's pretty small. It fits in a packet. You shove it out there on UDP, you get a response back. If you don't get the response, you ask again, or you ask a different DNS server, and eventually you'll either get a response back or something, you'll know that you weren't able to resolve that. And then there's a TCP domain protocol that's used if the request gets too big to fit in a single packet. It'll switch to a TCP protocol and actually set up a connection to the DNS server, ask its questions, get its responses back, and then tear the connection down. Also, like for zone transfers, where two DNS servers are communicating with each other. Say I'm managing my DNS on DNS server A, and I want DNS server B to be a secondary for that zone. If I make a change to the zone file over here, I need to send the whole zone file over there. That's going to happen over a TCP connection, not over UDP.
Right.
Then they'll both be in sync, and whichever one you ask, you'll get the correct answer back, right? So other protocols, the other ones I want to mention are, we talked about domain, HTTP and HTTPS. Everybody should be familiar with those. HTTP is the hypertext transfer protocol. HTTPS is the secure hypertext transfer protocol, which uses encryption on the connection to make sure that A, the server that you're talking to is who you think it should be, and B, the information that you're sending back and forth isn't visible to people who aren't you or it, right? So we can dig into those protocols later if we need to. But there's also like printer protocols. There's GPS protocol to put GPS data out on the network. iSCSI allows you to attach to a virtual disk drive from your machine as though it was a SCSI device on your computer. You can do that over Ethernet and talk to that. So if you've got a file server, you can export an iSCSI endpoint and connect to that from your computer and mount that disk. There's database protocols. There's tons of protocols out there. There's zillions of them, right? Everybody wants to do something new and different. They come up with a new protocol to do it. All right, some other protocols that happen at this transport layer, IP and CAP. What that does is it actually takes IP packets and puts them inside of other IP packets and sends them over. Okay. And you can use that to like route from one private network to another private network. This is kind of the thing that VPNs typically do. They'll either use IP and CAP, they'll use IPsec, or they'll use GRE for that. There's EGP, which is the exterior gateway protocol. I talked briefly about BGP, the border gateway protocol. Exterior gateway protocol is related to that. It allows you to figure out what's near me, what am I connected to, and what is it connected to, so that you know how to route your information. If you've got only one network connection, no big deal. You just have a default route. You shove your stuff down that pipeline and you let the other guy worry about it. If you've got two network connections or more, then you need to be able to figure out which connection do I send this down. Sometimes I send it down both, and it may take a different route to get where it's going. Whichever one gets there first wins. That happens. OSPF is open shortest path first. IP is another IP encapsulation protocol, and Ether IP actually encapsulates the Ethernet packets, the lowest level, inside IP packets and sends them over the wire. So you've got, you could potentially have a TCP packet inside an IP packet, inside an Ethernet packet, inside an IP packet, inside another Ethernet packet getting sent out on the wire. It's all wrapped up in this kind of expanding shell protocol. So FT protocols lists a bunch of different protocols and how they work. All right. How does AREDN use IP? So we've talked about AREDN in the past. AREDN is the Amateur Radio Emergency Data Network. The concept is to use Wi-Fi wireless ISP equipment to do IP networking stuff on amateur radio frequencies. Okay. So AREDN operates on net 10. All AREDN devices or addresses are on net 10. The addresses are automatically assigned to each node based on its MAC address. That address is hardware assigned by the factory that manufactured the device. Can you change it? Maybe. It depends on the device. But in general, you want to use the MAC address that the device has. AREDN operates as a flat network, no subnets. So you've got this net 10. Everything that's on there can talk to everything else. So it's on the same network. Okay. So that's kind of the idea of the mesh network, is that it's all one network. Now, it does support LAN devices, which are kind of subnetted sections of net 10, but the AREDN routing takes care of the mapping. So it looks like those addresses are on the big network as well to every other device on the network. So you don't have to think about that. It all just works. Okay. Yeah, it's weird. You can actually do natting as well, where you can have a subnet that gets natted to the address of the router, but most people don't do that. Uh, AREDN uses a special routing protocol called OLSR, Optimized Link State Routing, to figure out what the best way to get from node A to node B is. So each node knows everything that's on the network and how long it takes to get from node 1 to node 2, and how long it takes to get from node 2 to node 3, and how long it takes to get from node 3 to node 4 and back to node 2, and so on. It's all known.
So the initial, like when it starts to route somewhere, it's time based, not SNR based, is that correct?
It's both.
Oh, okay.
Yeah. So it actually takes advantage of knowing not just the time that it takes to send it, but also how good of a connection it is. So, because it wants to use the best connection that it can get.
So it does take.
So it does take both into account. What it ultimately does is through some manipulation, it identifies a weight for each, and I mean like a weight, like how heavy it is.
Yeah, no,
For each connection, right? Not a wait 5 seconds, but a wait as in how much that connection costs, essentially. And so it picks the route that gets the packet there most effectively. And remember, each node may have 3 nodes or however many that it talks to directly. And so it may say, well, it's best for me, from what I know, to send it to this guy. So I'm going to send it to that guy. Now, when he gets the packet, he knows what his routes look like. And so he might decide to send it a completely different way from the way the original node was going to send it. That's all done by each individual node as the packet moves through the network. So
Bridge two nodes, say on different channels. And that are previously existing, does it deconflict possible duplicates or?
well, there won't be any duplicates, right? So there's the packet will get there. If you get the same packet, if a node receives the same packet from multiple sources, the first one that got there will win.
So
Okay.
if I had a big node that was happening on one channel, not a node, a whole network, and a network that was all happening on a different channel. And
Those are 2 separate networks.
Bridge them.
So you had something in between them that's connecting the 2 of them together. Whatever that thing is going to know, in order to get to those networks, I have to go to this guy.
Oh, okay,
So it handles that, right? And those ones coming back, it knows I have to go through this guy to get to those guys, right? So that routing will happen from node to node. Each node doesn't have to know everything about the whole network. They typically do, but they don't need to know everything about the whole network.
And he just needs to know who he needs to.
Who's the best guy I should give this to? And then I'll give it to him, and then he'll say, who's the best guy that I should give this to? That's why the mesh network is self-healing, right? Because if a node goes away and I'm over here and I'm saying, well, because I know that node is there and that's going to be the best way to get over there, I'm going to send it to this guy. And this guy says, well, geez, I don't have a connection to that node anymore. But for me now, the best way to get it to that guy is to go this way, and it'll get around to that guy, right? So the network is self-healing in that fashion.
Is there any way in IP to say, like, say I have a node and I connect a little service to it, right? It's running on a computer. And then I want to duplicate that service on a different computer so that if this node goes down, it goes to that one instead, but sort of thinks it's the same thing.
That has to happen at the application layer, okay? So your protocol that you're using needs to be smart enough to handle that failover, because there's no good way. There are like aliases that you can use in the DNS to kind of do that, but that's one of the areas where I've been trying to rack my brain for a PBX system that can run in kind of this distributed model where I've got like 3 separate PBXs on the network. And if I only have one, everything's great. Everything works until that node falls off the network, and then nothing works, right? So what I want is some way to have more than one. I haven't found a PBX system that is smart enough to handle
Yeah,
that.
the only way I could even think about doing it would be a traditional load balancer and keep
Yes.
everything in the same sub.
You could theoretically do that. And that may be the way we end up going with services like that. I don't know. We'll have to see what we end up with. There's so much to explore with AREDN that we could talk for 2 hours just on AREDN alone. So
Can we
the
do
things
that
that
in
we
another
can
meeting?
do with it. We could do it in another meeting, yes. And I've done like an intro to AREDN, but now that I've been getting into it more, I know a lot more than I did when I wrote that intro presentation. So yeah, it's really cool. You can do some really cool stuff with it. And when you can think about, well, I can run this on amateur radio frequencies with more power than just the standard ISP Wi-Fi power, because amateur radio operator, I can do 1,500 watts on that thing
Well,
if I want to.
where can you get a device that operates at those?
You can you can build a gain antenna that can really crank out the power for you, right? Because it's the power as it leaves your antenna. It's not the power of the device that you can go on, right?
Maybe just before you finish at whatever that is, will you mention or comment on the best, if someone wanted to take a normal packet radio system and connect it, and what would be the best way to kind of go about
All right.
doing that?
We're going to hit packet radio in a minute. So if we, gosh, we're way over. You guys still okay?
I'm good.
All right. Okay, so with AREDN, each node has a LAN interface, and the LAN can be configured as either disabled or NAT. We haven't really talked about NAT yet, but we'll talk about it in a sec. 1, 5, 13, or 29 hosts. Now remember, when we talked about subnetting our network down to some number of hosts, and we said, if I subnet it down all the way to a /30, I've got 2 hosts that I can play with on that network. Well, it doesn't do me any good to have only one host on the network. I got to have somebody to talk to. So when AREDN's configuration talks about one host, the other host on that network is the AREDN node itself. So it'll say, well, there's one host on that network. That host is the other thing on the network, right? When it says 5, there's really 6. One of them is the AREDN node itself. When it says 13, there's really 14. One of them is the AREDN node itself, and so on. So you can do disabled NAT 1, 5, 13, or 29 hosts. And the way it's set up is if you change it from 5 to say 13, it picks a different network than the 5 network. So your IPs will be different on that network than the ones on the 5 network were. Now, if you go back to the 5, it should go back to the same block that it was using for the 5.
Right.
You got a question?
No, I did notice that, and I also noticed I set some static DHCP, and it actually kept the mappings.
It does keep the mapping, yes.
So
It's
so
smart
I
enough
didn't
to
have
do that. The
yeah.
user interface is smart enough to do that.
Yeah, that was
Yeah.
really nice.
Yeah, so when you set it to disabled, that basically turns the LAN off entirely. If you set it to NAT, then it uses the 172.27.01/24 subnet for hosts on the LAN, but it maps all of those into the node's AREDN address. So it hides the presence of those hosts, and other nodes on the network can't talk directly to them unless there's a port forward to them.
Right.
Okay. If you're using 1, 5, 13, or 29, those hosts on the LAN are on the mesh, and any of those LAN hosts can talk to any other host. There is a knob you can flip to disable that if you want to. You can not propagate those LAN ports. There's a checkbox. Yeah.
Yeah.
Do not propagate basically says don't let that outside of my network. Yeah. Yeah. So let's see, we said the node itself uses one of the available addresses. The LAN addresses are in the net 10 AREDN space and are routed with OSLR just like the node addresses, except for NAT, in which case they're hidden from the node. NAT is network address translation. And so like your home network is on 192.168, whatever, right? The router actually maps using network address translation all of your outbound connections to the router's IP address on the internet. And then when connections come back or data comes back, it maps that back to the appropriate host and port on the inside. And it does that transparently to you. That's why we can actually still use IPv4 because they developed this NAT protocol. Because otherwise, we'd have been out of addresses. Every machine had to have its own address and they all had to be unique. Can't do that when you run out of addresses, right? So that's what NAT does. AREDN nodes also have two additional interfaces, the DTD interface and the WAN interface. DTD is used for direct connections from node to node. So it looks like a regular internet internode link. So if you've got two AREDN nodes at your site and they're connected to each other by wire, it will look like a really fast, really inexpensive connection between those two nodes.
Right. That's like when you take that MikroTik 5 route,
Yes,
five hub, and you put it
and you plug it in the PoE port,
Yeah,
that becomes a DTD port, right? And so it's on the wire. It's always going to be the best choice for moving packets from this node to that node. It's always going to pick the wire. It may be able to see that other node on RF as well, but it's never going to choose to use that over the wire because the wire is going to be much better. Okay. And then the WAN is used for connecting to other networks outside of the mesh. And the idea there is if you've got your AREDN device attached to your home network, that is done through the WAN port on the AREDN device. And so you can actually connect to that AREDN node's IP address from outside from your home internet. And you could even port map something to come through from outside of your home all the way through into the AREDN network if you wanted to.
That could give you internet access if
It would give you internet access, and you can choose if you want to grant that routability out of your node through your network or not to other nodes on
Jan,
the
I'm gonna
mesh.
push it out there right now. I'm gonna set up tunnels to my internal router so that we can test stuff. I put a Proxmox behind mine and I'm gonna run virtual servers
Awesome.
behind it.
Awesome.
So
I'll
put that on the mailing list. So
Yeah.
we can start.
Get that out on the mailing list. Yeah.
Turn on tunnels once you have an object. So
The old UI didn't let you, but the new UI does.
I can flip it on and off.
Yeah, and you can delete them with the
Yeah.
new UI, which the old UI, you could not delete them once you created it. You could change it to something different, but you couldn't make it go away entirely.
Reserved addresses, is that what you?
No, I'm talking about the node to node tunnels outside of outside of the
The
mesh.
only way I do the old UI was you had to get the shell, get into the shell.
You could get in and muck with it by hand, yeah, which is terrible.
Yeah,
That's why the new UI is better.
I love the new UI.
It gives you so much better capability. So WAN is used. It will actually, allow you to connect to internet stuff from the mesh if you let them, right? All right. So essentially, on a given node, there's four interfaces. Remember, we talked about the difference between interfaces and ports, and this is where the VLAN stuff comes into play, right? So, say you've got your HAP, which has 5 Ethernet jacks on the back of it. The first one is the WAN port. The next 3 are LAN ports, and the last one, the PoE one, is a DTD port. Well, actually, all 4 of those could be either LAN or DTD, depending on what you plug into it. Okay. And then the other interface that it has is the mesh interface itself, which is the radio, right? So nodes that don't have a mesh interface will still have a primary mesh address, which they'll refer to as the no mesh address.
So that's why port 1 on the HAP says internet above it, right?
Port 1 is the WAN port, so you would plug the internet in
It
there.
says internet.
Yeah, exactly. Some hardware so has multiple physical ports, and some of these ports can be bridged together into those named interfaces on the inside, the logical interfaces. And VLANs are used to multiplex multiple networks, multiple interfaces onto a single physical port. Okay. Let's see. So on my HAP node, it has 5 Ethernet ports. One is the WAN port. The other 4 can be LAN devices or DTD links. Port 5 also supports PoE. So I have my LDF5 plugged into port 5, and that shows up as a DTD link. The WAN on my node is the connection to my home network. And remember I said my home network is on 192.168.50, and it got IP 192.168.50.193. And that's a /24 network. My home network is. And then the LAN gets this 10.225.133.187 as a /28, which is identified as a 13 host network in the UI, right? Really 14 hosts. Remember, /28 gives you 16 addresses. The 0 address is the network. The 1s is the broadcast. That leaves 14 host addresses. One of those is used by the AREDN node itself. I have 13 available for anything that I want to plug into it. And then the DTD is a /8 network, 10.95.24.91. That's assigned automatically by the node based on its own MAC address. And any addresses on that interface are mesh routable addresses. Now, the way the VLANs work is VLAN 2 is always the DTD VLAN. Okay. So if I have my LDF5 and it only has one physical port on it, that port can be both, can be WAN, it can be LAN, and it can be DTD. It depends on the VLAN tagging coming off of that port. Anything that's untagged is going to be LAN. So if I plug some device that doesn't know anything about VLANs into it, it's going to appear as a LAN device. So when you first configure your AREDN node and you plug your laptop into it, it's coming up on the LAN, and you'll get a LAN IP address, and then you can talk to the node through that.
Can you also confirm something for me?
Yeah.
My understanding is also WAN is VLAN 1. Is that correct?
WAN is VLAN 1. So if I have that cable, that single cable coming off of my LDF5, if I run that into a switch that's VLAN capable, I can say anything that's tagged as VLAN 1, go over here, and that's going to be my WAN connection. Okay. And the DTD is VLAN 2. The untagged is going to be LAN. Okay. Does that make sense?
Yeah, I'm good.
All right. Now, on my HAP, I have the radios turned off because it's just sitting in my basement. There's nothing else for it to talk to. My LDF5 is sitting outside. So it has a no mesh address of 10.94.24.91, and that would be the mesh address of that node. So that node can be on the mesh, even though it has no radios, because it has a mesh address.
And the DTD connection to the.
And it has a DTD connection to the LDF5. Right, exactly.
Is again, just to reconfigure that /32, is that the same /32 for every radio?
Yes.
Okay.
Yes. They will all appear as a /32, right? So it's basically
What I'm saying is the dotted fours. Is that the same dotted fours, or is it going to generate that based off the MAC?
Oh, yeah, it'll be based off of the MAC.
Okay.
Yes. So on my LDF5, I have a single Ethernet port, but it uses the VLANs for this, right? So the WAN network I'm not using on that, but if I did, it would be on VLAN 1. The LAN is the untagged. Any packets that are not tagged with a specific VLAN are going to be on the LAN, and this is set up with a /29. I could probably just turn it off entirely because I don't really use it on that node. And then it's got the DTD connection, which is the other end of the DTD link to my HAP. And then it has the WLAN 0 address, which is its mesh node address. Okay. So you can see how those are different between a device with a single Ethernet port and a device with multiple Ethernet ports. All right. So VLANs. VLANs are a way to have multiple interfaces on a single physical network connection. So remember, when we were talking about our terms up front, we talked about the difference between an interface and a port, where the interface is like a logical connection to a network, where the port is a physical connection to a network. Okay. So AREDN uses these VLANs to logically separate networks for different purposes, even on only a single Ethernet port. Okay. VLANs happen at layer 2, so switches can understand VLANs and do things with them. Some switches are too dumb to do that. They don't know anything, right? They're just packets are packets. They don't care. Smart switches may support VLAN tagging and allow you to assign specific ports to specific VLANs, and even say, if I have untagged traffic, tag it with this before it goes anywhere. Okay. So I can actually tell the switch, oh, if you see an untagged packet come in, put this tag on it, and then it will be that tag as it goes through the network. Okay. So here's a sample AREDN VLAN config. This gives you traffic isolation with VLAN. So there's several nodes in play here. There's node 1 and 2 are nodes. 3 and 4 are nodes. Those are AREDN radios. Okay. Then 5 is a camera and 6 is a PC. So I have these plugged into a switch. Port 1 is VLAN 2 for, remember, VLAN 2 is DTD. And so anything that's on VLAN 2 is going to be able to talk to each other as a DTD device. So I want all my nodes to be on VLAN 2. And then the camera, I only want visible to nodes 1 and 2. I don't want nodes 3 and 4 to even see it. So I set the ports up for the port for the camera up so that it doesn't go on the VLAN. This is a bad slide. I'm just going to skip this one. It's too confusing. I'll talk about that in another meeting when we actually dig down into some of the AREDN stuff. Let's talk for a minute about firewalls. Firewalls are used to protect your private networks from the outside. You probably have a firewall at home. It's built into your home router. It probably runs that NAT protocol. We already talked about NAT and how it works, so I'm not going to dig into that too much. If you want to run multiple services or servers inside on your home network and access them from the internet, you have to do port forwarding. You have to configure a port forward on your router that says, if I receive traffic on this port, I'm going to send it to this particular host inside my network. You might need to do that if you're going to use Echolink on a machine at home. The problem with Echolink is you can only do one. You can only have one Echolink machine in your network because there's only one way to port forward it. It always comes in on the same port. That's a problem with Echolink. Echolink could be modified to use UPnP, which is universal plug and play. And that basically allows internal machines to tell the router, by the way, I want to receive incoming connections on this port. So when they come in, please send them to me. And then the router maintains a table of that. There used to be some issues with security at UPnP. A lot of people were saying, we'll turn it off. Nowadays, it seems to be on all the time. I think they worked out the bugs and stuff that caused problems with that. Okay. If you've got a smart home like your Ring camera or doorbell or something like that, where you've got a Google or Alexa smart speaker, those don't run as a server. They run as a client, and the server is out on the internet. So when you have your Ring doorbell and you have your Ring speaker that dings when somebody pushes your doorbell button, what's actually happening is they push the button on the doorbell, and the doorbell sends a packet to Ring, and then Ring adds that to a queue, and your doorbell ringer box is asking Ring all the time, hey, do you have anything for me? Hey, do you have anything for me? Oh, look, you've got something for me. Ring the doorbell. Ding dong. Somebody's at the door. This happens so fast that you don't even notice it happening. But if your internet's down, suddenly your doorbell doesn't work anymore. So that's a thing, right? But they don't put you at risk of running a service in your home, but they do consume more of the network and more computing resources at wherever the server is for every device that's out there. So you wouldn't believe the stuff that they go through to make this stuff work on their servers. It's really pretty amazing. I've worked in that environment a few times, and there are some cool things that happen. Some business firewalls will also block outgoing connections if they're not on a certain allowed list. So you might get a message saying, oh, you can't go to that site, or SSH just doesn't work for you from work.
Isn't it do that a lot?
I don't know. It might. it might block some stuff. I don't know. I haven't.
Most everybody in network administration, tell me if I'm wrong, it's usually blocked by default, only if you need it. So,
Okay,
Okay. So if you need something, some protocol to get out, you need to talk to your network admin to allow that. And getting that to happen in a corporate environment, if your company has 6 people, it's probably not too hard. If your company has 6,000 people, it's probably not going to happen. Right. So just keep that in mind. VPNs allow you to tunnel packets from one network to another network. VPN is a virtual private network. It encapsulates, remember we talked about that IP and IP encapsulation? It encapsulates the IP protocol inside another protocol, either TCP or UDP, and can ship that around the internet to some other place and allow you to connect one network to another network. Some of them use their own protocol. Some of them run on top of HTTP, which is pretty cool. Nobody's going to block that. However, they may do some deep dive, man in the middle kind of weird stuff. But yeah, you know exactly what I'm talking about.
yeah, I had to do it today.
Yeah. So there's even stuff that will man in the middle intercept your HTTPS traffic by faking a certificate for your host on the inside. So just keep that in mind. If you don't control the network, you don't control the network, right? So you don't really know what's necessarily going on that network, and you have to decide how much you're going to trust it and how much you're not going to trust it. Let's see. Okay. Some people will buy VPN access to hide their traffic or make it appear to come from some other location. You'll see this with people doing like Netflix. Netflix has a catalog of movies available in the US, and they also have a different catalog of movies available in the UK, for example. So if you get on a VPN where now it looks like your traffic is coming out in the UK, suddenly you can access that UK catalog of movies, which you could not access from the US because of licensing and whatever. So people will do that to kind of evade that. All right. What about packet radio? Okay. Packet radio uses a different protocol. It's called AX25. It's based on the X25 protocol, which all of the reliable delivery stuff, the checksums, and all of that jazz are boiled down into the transport layer of the protocol. So down into the network layer of the protocol. So down below the that transport layer or that application. You have your application, you have your transport, then you have your network layer and your physical layer, right? So X25 operates down at that lower level. It does all those checksums and it's happening for you. It's designed for slow, lossy networks where you might shove a packet in there. It will handle resends automatically for you. It will do whatever is necessary to get that packet from one host to another. One thing you'll notice if you're looking at AX25, the address is your call sign. It's not a number, it's your call sign. So that's kind of cool. If you look at an interface list on your device and you have an AX25 interface, your address will be your call sign. You can tunnel X25 and AX25 packets over TCP/IP. Remember, you can encapsulate anything, right? So you can encapsulate that stuff in a protocol and shove it over the internet. And you can also encapsulate IP traffic inside AX25 packets. And that's been done before with packet radio. So I'm not going to talk.
Have you done a TCP dump on X25?
I have not. I bet it's really cool. Really interesting. So I'm not going to talk any more about packet radio because that's outside of the scope for this conversation. IPv6, remember we talked about IPv4 versus IPv6. The big changes with IPv6 are the size of the address space. IPv4 had 32-bit addresses. IPv6 has 128-bit addresses. So this is how many there are. What did you say it was? decillion or something like
Yeah,
that.
yeah.
Yeah, so
And just so you know, that's 3.4 times 10 to the 38.
yeah,
And there are 10 to the 82 atoms in the universe.
yeah.
So
So
it's
so there's
not
a
enough.
it's not enough.
Not
Okay,
enough.
okay.
Yeah. The best you can do, 10 to the 50 is the Earth. Okay, so it's less than that. The human is 10 to the 28th. So human and a half, all the atoms in Sherwood and I
Could have their
could
own
have
IP
their own
address
IP address with
with
there you go.
IPv6, right? So some of the functionality that was implemented at the application layer in IPv4 is now implemented directly in IPv6. Security is built in. In IPv4, you had to use a protocol called IPsec that wrapped things with some encryption capabilities. Quality of service is built into it. Multicast is built into it. And it has a much simpler header, so routers don't have to do as much work as they figure out where they need to push things. So it's really a better protocol. And if you can use it, a lot of ISPs nowadays are giving out IPv6 addresses. Comcast will, Xmission will, a lot of them are doing it now. So if you can use it, take advantage of it and, check it out.
I reserved 1 billion IPv6 addresses.
It's essentially
it's nothing.
it's essentially transparent to you anyway because you only care about the host names. Remember we talked about that domain system? It can map those host names into IPv6 addresses as well as IPv4 addresses. All right, that's it. Thank goodness. We are only an hour late. I should have probably broke this into 2 presentations, but oh well.
Well, we know for next time.
Thanks for sticking around. I appreciate the interest, and this will go up on YouTube probably later tonight. I'm going to stop the recording unless there's any questions real quick.
And Jim, like I said, my offer will stand. I'll put an email out on the Salt Lake Mesh groups probably tomorrow after I get done with work and wanting
For tunnels into your AREDN.
about setting up tunnels.
Okay.
And then I'll individually message everybody with login info.
Sounds good.
So could you just repeat, starting with the third slide and go forward?
Sure. Why not? Okay. All right, I'm going to stop the recording. Thanks everybody for